Hi. So, let's see. We're going to today. I think we will finish the sampling distribution, and then when the time left, we'll cover some basic Python. If we have time. If not, then you can attend the one that optional class tonight. If I don't have enough time to cover the Python, because there will be 3 hours. Things that I'm doing in the oh, is it there? No. Hi. Is the mic on? No. Hi. Oh, sorry. Where we are the test? Yes. Okay. Okay. So so let me first quickly finish this. I think we are almost done, except the fact that there's a new thing we covered there, almost done. So it's something that not very complicated. So we'll finish this one, and then if time left, we will cover some basic Python. So the idea of this is the introduction to the second part of our course, which involves studying using data to do analysis. And in particular, we focus on mean and variance. For those people in the Zoom, can you hear me? If not, then let me know. Otherwise, I'm not sure, because it seems okay, but not entirely clear. But anyway, so the idea of this is basically you are going to study the population. You want to know things, especially mean and variance in the population, the things you want to study. But the fact that you don't have everything there will be a problem. You're only able to study a subset of the problem. Okay. For example, you want to know the income of everyone in China. That would be impossible because of 1.4 billion people. So what you're going to do is to collect some of the people, ask some of the people in China, and hopefully what you obtain, what you learn from the small stuff, which is called sample, would be representative. And in our class, we restrict ourselves what we call simple random sample, which essentially said each observations in the population will have equal probability being selected, and the selection of one doesn't preclude the other one, so the independence. Okay, and the important properties you learn in this slide is to remember is each observation the same mean and same variance, and covariance being 0. That will serve the basis point for the proof of the central limit from law of large number. All right. And here we define what we call statistics. Right. Statistics is we define it as the way that is a function of the random variable. Right. By function of random variable, it means that it's also a random variable. Okay. So statistics like sample mean, sample variance are random variable because it depends on what sample you got, right? Suppose you ask the income of people. If you're able to get only rich people, then your sample is with a very high mean. Or if you get very poor people, that will be where the sample mean will be very low, right? If you get average people, will be average. So that's the idea behind it's a random variable, and that involves probability, right? Depends on who you got, who you talk to, and that's the reason why what you learn from the probability theory will be important. So here we have sample mean, right? Sample mean is just standard, the mean that we have, right? So what is the special about this? Okay, this is we use this sample mean as a random variable. Remember, it's depending on what sample you got. And we'll talk about in the next topic, this next week, that this sample mean is a nice to estimate the population mean, right? So that is from the basis of what we are doing, right? Because what we want is to use we want to find the mean, the population mean, the average income, average purchasing power, but we really don't have the idea of what happened in China where 1.4 billion people. But what we're going to do is to get a sample and get an estimate of that, right? The sample mean, and then sample mean will be used to estimate the population mean. Okay. And here, before we talk about next class, we give you the idea about what the property of sample mean, right? And the first thing is what we call biasness, which said the mu is exactly the expectation of the sample mean. Essentially, what it meant is if I do the sample many times, which I don't, but suppose we do, we repeat this process many times. Okay, we have many sample mean, right? Because each time we have sample mean, then we have many sample mean. Average of this sample mean is same as the population mean. Okay, suppose we have many resources, right? And we're able to repeat this procedure many times, and average of those will be the thing we want. Okay, and this is potentially not for business, but for science discovery, right? That's how you do, right? Say one lab will be doing this and the lab doing that, and overall the average or the summation or the aggregate knowledge from all the labs, it actually discover what we want, right? That's why we need so many schools, so many people to do research, right? Because if you have enough research, then it should be fine. Okay. Now, there's a graphical representation of this, right? Is you have the sample, right? And then each sample, we have sample mean and average of those sample mean. Okay. Turn out this guy will be exactly as same as the population mean. Okay. So that's the idea. And I'm not going to repeat the example because I think that would be fine. So the other one that we care is sigma, right? And is how accurate is our sample mean? Okay, and turn out that it is going to be the population variance divided by n. Okay, so it is very natural to see that because if the underlying population has a high variance, you should expect the sample mean has high variance, right? Because suppose the income inequality in China is very high, suppose, then in that case, the sample mean can vary, right? Because you can end up with very rich people, very poor people, right? But in the cases, if in 1.4 billion people, everyone has same income, right? Then no matter how you sample, how you get the sample mean, always the same, right? So it is inverse proportional to the n, right? But of course, sigma square, how we get, we don't know. But here it says, suppose we had sigma square, this is what we have, okay? We still don't know but that is the property that we have. We'll talk about how we had to handle this when we don't know sigma, okay? We'll talk about this immediately, okay? So after that, we have two important theorem, or probably the most important theorem in this class, besides Bayes' theorem. Okay, these are the two theorem that I think is the most important. When you learn statistics, especially this type, and these are the two important functions that basically serve for the basis of what we're doing. Okay, and the first one is law of large numbers, which essentially said one thing. Okay, if you look at the sample mean, okay, the sample mean will be as close as to the population mean if your sample size get larger and larger. Let me repeat the statement again. Okay, It just said I do a sample. If I extend the sample size, right? Remember, each time is a random variable, right? No matter what the sample size is a random variable. But essentially said when the sample size get larger and larger enough, the variation is so small, okay, such that it will be as close to sample mean as possible. Okay, so let me repeat the statement again. Okay, we draw it, it's easier. Okay. So the idea is the following. Okay, suppose you have a whatever data X random variable care, can be any shape, need not be normal, but can be anything, right? Can be anything, doesn't really matter. Okay, it turns out what it said is you can do sample mean, right? And sample is a random variable, and sample mean depend on the sample size, right? If you have just collect one, right, that will be same as this guy's, no difference, right? Because that is what simple random sample means, right? Just draw one guy of that, the same thing, right? The distribution of that will be the same as probability, right? But let's look at when you have this guy, what happened to this guy? This guy would be much smoother because the variance reduced, right? Remember, this is this over 2, right? So I don't know the shape, but it will be something a little bit more gentle, right? And what law of number said is when you go to very big, okay, n is big, there will be something, suppose sample means here. Okay, suppose sample means here. I don't know what it looks like, but it will be something like something concentrated at the center. Okay, and the bigger the n, there will be very squeezed in the middle as long as you get out larger and larger, basically at the center. Okay, so that's what it means. There will be no variation at all, right? When you get to the sample size larger. Okay, so let me read this statement because I think it's enough. It's good to get precise. Okay, but of course, looks very weird, but I probably have to explain a little bit. So what it meant is mu, okay, it's not a random variable, right? It's a constant. We don't know yet, but what it meant is the sample mean, okay, will be as close to the population mean as possible because the epsilon is any number, right? It's close to it. It means the following, right? Suppose this is the mu is here, okay, and I have n epsilon, any small number you give me. So this is epsilon plus mu plus epsilon, mu minus epsilon. Okay, what it meant is x bar is a random variable. It means that x bar can be anywhere here. Okay, and it said the probability is within this range. Okay, when n goes very big is 1. So it means that give me any small number you have, I can give you n large enough such that it's always within this range, right? So that is the idea of the limit, right? So give me any interval, no matter how small the interval you want to give me, I can always give you n big enough, the sample size big enough to make sure that no matter what you do, it's always within this range. Of course, I cannot ensure it's exactly mu, but as long as I have n big enough, I can achieve the distance is so close to the any precision I want. Okay, so that's the idea. Okay, it's not exactly there, but it will be as close as we want if we n as big as we want. Okay, so that means that is the idea underlying the statistics, right? Because at least there's hope if we're able to get a large sample size, the variation will be as close as to 0, right? The probability will become 1, right? Exactly inside. Okay, so that is the basis for statistics, right? But if you don't have this, then there's no hope to do anything, right? Because at least we know, although it's impractical, but we have to aware that when n is big enough, it applies, right? There's no more uncertainty there. Okay, the probability is no longer matters, right? Although X bar remain a probability, right? But it is saying that it's as close as we want. The next one is called central limit theorem. It essentially tells us, okay, how the graph looks like. Okay, we said from the law of large number, we don't know how the graph looks like. Okay, you list any shape we want, right? Can be up and down, up and down. As long as it's squeezed in the center, that's fine. And central limit theorem, of course, require a much stronger assumption, which we don't elaborate here. It will be saying that as long as certain conditions are satisfied, which you will satisfy for all the application you will be doing, it is saying the shape will be a bell shape, okay? Regardless initially what it is, okay? Let me repeat the statement again. Is regardless of initially the blue curve is whether it's a uniform, exponential, binomial, whatever thing you can imagine, it will end up the X bar is always a bell curve. Okay, it's a normal. Okay, so that is the central limit set. No matter what you're doing, when this is big enough, it's always bell. Okay, so that is the central limit theorem is talking about. And that's why we always call normal, right? Because normal is so common. And this process turned out to be getting an average. It's actually what you measure in the real life, right? Look at the IQ, it's average of many things, right? And your weight, your height, a lot of stuff, and the GPA or your exam score, everything is the average of many stuff, right? Whether you attend the class, whether you pay attention, whether you have a lot of stuff, is a lot of random thing goes on, right? How you feel when you do the exam date, right? Whether you have enough sleep, right? Or so on and so forth. Okay. Now this is central limit theorem, right? So it essentially claim the X bar will follow normal, right? And we learn the middle, the mean is this, the where is that is already there, right? So probably you worry about in the real life whether we have enough n, right? Because central limit theorem, law of large number both require very large sample size, and luckily the rule of thumb is more than 35, then it would apply. Okay, and probably you ask, okay, what happened to less than 35? Okay, and don't worry, you are in a business world, so it shouldn't be matter, right? If you are in other scenario, then you may worry about that, right? If less than 35, then you should ask your boss to increase your budget, right, to get more samples. So it shouldn't be a matter thing. Okay, and of course, probably you will know that how you do when you're less than that. There are many ways. Say there a lot of ways called say bootstrapping method, Monte Carlo simulation. A lot of method you can be done, but it's way beyond the scope of an elementary class to cover those. I mean, there are way to handle those problems. But it shouldn't matter for us. Okay. So let me talk about this binary data. Okay. It's not at all complicated. It's actually even simpler to what we are doing. Because of course central limit theorem applies, right? Because or law of large number applies, but there are other nice features without using them. Okay. So let me just repeat what it's about. Binary data is yes, no question, right? Do you like spicy food? Yes or no, right? Is tomorrow going to rain? Yes or no? Okay. It's trying to, you can imagine this, remember the random variable, right? So basically the sample space, you map the outcome to either one thing, 1 or 0, right? It's not the world is 0 or 1, but you just group the outcome into 0 or 1. So it's a random variable lead to 0 or 1. It's not exactly the world is 0 or 1. Okay. And the thing you're interested in that case is usually called population proportion, right? Imagine you want to know how many female in CHK, right? For undergraduate students, okay? The proportion is pi, okay? And the population mean will be pi, right? The variance is pi times minus pi. Why? This is just come from binomial trial. Okay, if for CO1, 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 the variance is pi times 1 minus pi. Okay, I'm not going to prove it, but this is directly fall from that. Okay, you can actually check it. If a bunch of CO1, you can prove it. Okay, nothing very deep there. Okay, and or if you don't want Bunoni, right? Or it can be same as binomial, but anyway, the same thing. Okay, so that is how the binary data is actually every observation is a Bunoni, right? And if you learn every observation is Bunoni, then it means that if you have observation and sample size, then it's a binomial. Okay, I'm not going to do the proof, but just the terminology. Okay, when you're binary data, sample mean is sample proportion, right? Because you have a bunch of CO1, right? Suppose a case to make it easy. Suppose you have n equal to 5. You ask 5 people, okay? And you have female, 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 male, and male, okay? And that's what you got when you go to canteen. You ask their gender. This is what you got. Then the sample proportion will be, suppose you have consider female is 1, right? 1, 1, 0, sorry. 1, 1, 1, 0, 0, right? And the sample mean, right, will be just 1 plus 1 plus 1 over 5, right? So this is exactly the proportion, right? That's why I call sample proportion. And in the textbook, in many textbooks as well, we will denote the sample proportion by P, but this is just sample mean. Okay, there's nothing with the P is just the name. Okay, but why we care about the name? First, this everything follow directly from the expectation of the sample mean, right? Sample proportion will be same population proportion. Okay, and the variance is also the same, right? Pi times 1 over n. There's nothing new here. Exactly putting what we have there. Okay, and the central limit theorem also applies, so everything the same. Okay, that's nothing special here. Okay, the only thing special here is, as I said, okay, this guy, right, x bar, okay, n times x bar, okay, is actually sum of the xi, okay, and sum of xi is actually binomial, okay, and turn out is a very interesting thing is how you relate binomial and normal, okay. Of course, this is a something that probably you wouldn't care if you are not QFN student, but at least we know that even binary data, we still can do central limit theorem. The only thing you have to worry about this is this approximation would work. Okay, it's different from the case before where n is more than 35. We have to usually make it work. The rule of thumb is n pi, and n times 1 minus pi is more than at least 5. Okay, so that has to be something careful. That's why I have to spend a few slides to talk about this. Okay, it says when data is binary, the rule is slightly different, right? Because n is more than 35 is different from this one, right? Because it depends on the pi is, right? Is that okay? Suppose you believe the CHK, the pi is around 60 to 40-60, right? So its pi is around 40 to 60. Well, suppose that is what you think, right? Then you would say what is a good approximation? N prime, right? N prime is more than 35, right? N times 1 minus prime is 35. Sorry, more than 5, right? Sorry, more than 5. Okay, and we have like pi is like 0.4 to 0.68, right? And you can pick the you divide both sides, right, by 0.4 and 0.6, right, because they're complement, right, and 1 over 0.6 is more like 0.6 is like 205, right? So would be something like more than 10 would work, right? So if you have like 20 to 30 people, then you would work, right? It's a good approximation using a normal. Okay. But okay. So just later you will see when you have binary data, things are slightly different. Okay. And this is I have talked about that. Okay. We're going to talk about this. But here we talk about the last one. And then we'll break enough after we talk about Python. Okay, because I think we're done for this. This is very simple. Okay. So we have set the central limit theorem is x bar minus mu over sigma over root n is close to 0.1. Okay. And so now the problem is we don't know sigma square, right? It's something that we don't know. Of course, we have some guess, right? We can have some idea what it is. What we have is the sample mean, sample variance, right? And later we justify why we have this guy, okay? But suppose we have n-1, right? The sample variance, okay? This is the best thing we know to estimate this guy, okay? And we explain next class why this is the case, okay? And the question is we want to know how it looks like, okay? It's going to be normal, okay? It's a bell curve, okay? And it turns out it's a hard problem, okay? It's not something that not easy to figure out that guy, but turn out someone proved this guy. This guy turned out to be again a bell shape, luckily. And this is a bell shape, but the tail will be longer. So it will be instead of a Z, it's a student T, the T distribution. I mentioned last class, 2 classes before. So this guy turned out to be a T distribution. Okay. But before I do that, I need to make some assumption. Okay. In general, this is not a bell curve if you do not make further assumption. Okay. So what we need now, okay, remember central limit theorem doesn't require any assumption. Okay. Basically, there's some assumption, but it's not big. But here, if we want to know this shape of this guy, and later you will see why we need this guy, because we want to make some guess for the sample mean. Okay. But we need to have assumption is underlying distribution is a bell curve. Okay. So it's a pretty, I don't know, maybe you say strong or weak, but it holds for many cases, may not hold for some other cases, but we need to make that assumption is the underlying must be a bell shape. Okay. So this slightly different from here, right? We have a bell. We must have a bell. Okay. We need to have a bell shape. Okay. We need to have assume underlying is a bell. Okay. Of course, law of large central limit theorem apply, right? Because a bell, it must be a bell. Okay. The sample mean is a bell. Okay. And it doesn't require approximation, right? Because when a central limit theorem require n go to infinity, it's a bell. But here it said because the data underlying the population is normal, is also normal. Okay. So this is the result that I think we use the most often. Okay. The proof is the following. Okay. So this guy would follow a T distribution. Okay. It's a bell curve. But this bell curve is rather complicated in the sense that it's not single bell curve and the bell depends on n. Okay. And you expect this happen because when n go to infinity, right? And that turned out to be a bell, standard bell. Okay. We have a T bell, a feather bell. Okay. Feather tail bell when n is not big enough. Okay. And here we have some new terminology called degree of freedom, which is something you never know what it means, but just n, okay? And we don't explain why it's called degree of freedom. It's way beyond the scope of our class, but just a parameter n, okay? And when we have sample size n, we use n minus 1, okay? So that is the idea. So I'm sorry, we can't explain it, just a rule that we need to follow, okay? So I think it's good to give example that would give the idea how to figure that out. Okay. So with population, follow a bell with mean 5. So this is a question. Okay. Okay. The reason why we don't know sigma, if we know sigma, then we're done. Okay. We can just use the we know sigma, then the sample mean will be just sigma square over n, right? So we have the random sample of size 100 and the sample weight is 8, then what the sample mean less than 4.5, okay? So the question here is this, okay? You ask why we care about this guy. Very soon we will be talking next class and onward is we want to estimate the mu, right? That's something we want to do, okay? But to do that, we need to know what's the property of our sample mean, x bar, okay? Now we know it, then we can do a lot of estimation next class. And then we do hypothesis testing and do a lot of things based on how the sample or how the statistic looks like. The sample mean, how the sample mean behave, right? Because if we know the probability, right, know the shape, right? That's the basic thing. We know the shape, then everything is done, right? Then we can do a lot of things. So I'm sure that now you are probably confused why we do this because it's highly abstract, right? But the thing is because we need this knowledge to do the next class. Okay. I'm sorry, bear with me. But I mean, this is just the last part that we do theory. From the next work, then everything is applied. So this is the class. I think it's the most boring class because a bunch of theorems. Nothing we apply because why we care if the sample mean less than 4.5, right? Why we care that? But you soon later know this is the knowledge that we build on to estimate. If we want to learn the population mean, right? This is the process that we to learn. Okay. And we want to know this one, okay? And how do we proceed? Okay. And one thing that based on the theorem, okay, the main theorem, okay, is this guy. The sample mean minus 5 divided by 8 over root 100, right, is equal to t distribution. Okay. Remember the formula is x bar minus mu over s over root n, okay, or square root over s square over n. Okay. So this guy, right, is T99. Okay. I'll talk about T99 very soon, but it's a bell. Is the bell the number 99 bell, T bell? Okay. Bell is a T bell has a number. Okay. It's a serial number 1 up to number infinity. Number infinity is set. Okay. Number 1 is very big tail. Okay. The larger the number, the smaller tail is. Okay. And if you want this less than this, okay, what we're going to do, right? We'll do the same operation on both sides. We'll do, right? So we have inequality here, 4.5. Okay. What we do is we can inequality, right? So we can subtract both sides minus 5. Okay. This inequality is the same, right? So there's nothing changed inside the inequality, right? X bar minus 5 is the same thing. Okay. And what I do is divide both sides by square root of 8 over 100. Maybe use other color. Okay, and what we get is the left hand side is T99, right? This is T99, and the right hand side is negative 1.6 right? So that means that we have a number, right? And that's a bell curve, as I mentioned. It's a bell, the T bell. T99 is still a bell with a peak at 0. Of course, this 99 is much fatter than the Z, right? If you have the standard normal, it'll be something like this, right? Standard normal will be something like much fatter and much taller in the, right? If you have a Z, okay? So we have another, look at the other table, look at the bell, okay? So how do we do that, okay? I have a T table, I think in the slide, okay? So T table is rather complicated object, okay? And you first need to read, usually the table, you need to read, if Excel is easy, but if the read, you to read it, you read same, look at the row first, look at the number of row first, okay? And here I start from n equal to 1 up to n equal to 20, okay? And then I have 21 up to 160 and 180 up to 5,000, okay? And unfortunately, we don't have 99 here, okay? But doesn't matter, we mean 900 because 900 is similar, okay? I'll tell you, but you will see it's easy to do in the Excel. I'll tell you immediately now, but when I just see it, okay? So how we proceed is 100, right? And remember the question is what? 1.768. Okay. 100 is somewhere between these two. Okay. Between these two numbers. Okay. Now, it's between this number, remember it's 0.1 and 0.05. Okay. Let's remember this two number. Okay. So what this graph tells you, okay, is T100, okay, not 99, but it essentially said this is 0 here, okay, and here is 1 minus alpha, and it's a alpha over 2, is alpha over 2, okay, and what it said is a two-tail, because look at the table. It mentions a two-tail table, typical table two-tail. Two-tail is 0.1 and 0.05. So alpha is either 0.1 or 0.05. Okay. So it means that the middle guy, okay, the middle one, the middle is either 99%, 0.99, or even 0.995. Okay. So it's 0.1 and 0.95, right? Yeah. Or 0.9 and 0.1 and not 0.1. It's 0.9. Sorry. It's 0.9 or 0.95. Okay. So is it 10%? Okay, on the both sides, or the 95%. Okay. So remember the question asks you what? Let's go back to the question. Probability that T99 is less than negative 1.79 something. I remember correctly. So somewhere here. Okay. And we know if we have the color. if this is 0.05, okay? So that means that if this guy is 0.025, okay? And this is negative 1.9, okay? And if this guy negative 1.8, okay? Then this is 0.05, okay, the left-hand side, right? Because the middle is 90% or 95, right? So the both are symmetric. So it's either is 2.5% or 5% within. Okay, so you can check the answer. It should be the same as we have, right? It's between 5%, 2.5%. Okay, but of course you are not happy with this. Okay, let me show the Excel. We do it quickly because Excel just one function, the same as the normal, and then we'll break. Okay, Excel, because it's rather simple. One thing we have is n is 100. Okay, we'll use 99, right? And n minus 1 is 99. So just make sure that you know what I'm doing. Okay, and I want the probability that x is equal to negative 1.73, I think, if I remember correctly. Is it? Am I right? 1.768. 1.768. Okay. Maybe I choose t, right? T99. Okay. Or t, that's fine. So what I want to ask is probability that T99 is less than 1.768, right? And less than that is just the, on the left hand side, it's just the big F, right? Everything on the left hand side is the big F. So it's very simple. We just T this, okay? Same as what we do, that this is always the left hand side. Okay. And then what we look is the left hand side X, which is this guy, B, and then the degree of freedom, which is just this guy, n minus 1, and false. Okay. And let me see. Okay, that should be right. Yeah, so I don't know why I have a problem, but now it's correct. So so that is the answer. Is that is less on the left hand side of the bell is negative 1.7. Okay, so it's now it's not entirely clear why we do this, but it will be soon become clear. Okay, after next class. Okay, so I guess that's end our first section. We have a break, 10 minutes. In the meantime, I will do you reply, and then after the break, we'll be doing some Python. If you have Python installed in your system, that will be fine. If not, then you may register your account in the Google Colab. We will do that. Okay. If you are using your iPad or what, you don't have the development, then you can just go to Google and just simply if your Google account, register an account, then should be fine. Okay, just go to here and then you can sign in your account, then it will be working. Okay, so let me do the U reply. Here, I just sign in. You can sign in, then we will be then you will be working with this environment. So this is the Python that you're doing, or you can have a Visual Studio or whatever is working. So no problem. But this is the one that I will illustrate. So please fill in, and then you can let me know. I'm going to pass a slow, but hopefully, you can tell me what the problem is, or I'll go around to ask any question you might have. By the way, I have look at the Python slide, which I see already. Go to the content and Python slides here. I'll go over that slide. Not everything. There's 200 page slide. I can't cover everything there, but I cover as much as I can. So let's see what we have from the UV pi. Should I minus one less than? So the idea is the distribution, the big F, okay, is always less than, right? No matter you do Excel or what, right? Just to remind you this, right? Some of you. Right? It's always suppose a bell curve, right? The question asks you, say this is X, right? A bell curve, right? X follow a normal, mu, sigma square, right? The question may be, okay, this is mu here, right? What's the probability less than this guy, right? This is, right? What's the probability that X less than or equal to A, suppose, right? And this A is here. right? A is here, right? So this is just f of a, right? Okay. And to remind you, okay, how to do this is either you can do one way, right? You can do the Excel, just norm this, right? A mu sigma true, right? That's what we do, right? Directly Excel will give you, or you can do normalization, right? You can change to z less than a minus mu over sigma, okay? And in that case, is norm this, I think standard s, and put z true. Okay, oh, sorry, not the z, but rather you put this guy, right? You put here that guy, right? Okay, so that would be the way for you to do if you want to the left hand side. Right hand side will be just 1 minus, okay? Because what you have in all the whatever table Excel is always given the left hand side, right? The displacement function is what they meant, right? Regardless of is a bell shape or non-bell shape or what, right? So you have to calculate the right hand side, okay? Some of you are doing the homework is struggling. I do understand, because homework is make sure that to force you to think whether you know what you are learning, okay? Because math is always, as I often mention, the analog. It's like swimming, right? I teach how to swim. On the ground, there's no point. I mean, there's no use unless you actually go to swim. So I think already the exercise already bare minimum that you need to know. And also that's what I expect you to do in you're able to reproduce something similar in the final test. Okay. So if you understand what's going on in the assignment, you shouldn't have an issue for the exam. Of course, as I said, at the end is this, because everyone almost know if you know the assignment. So what is assessing is the speed, how fast you do the home, if you understand all the assignment. The question is who get A minus or B plus is basically the speed, right? If you know well, then you do faster. You do know well, you don't know that well. So I will have more question than you expect to have, right? So if you do fast enough, then you'll be fine. Okay, so that's how I differentiate, because otherwise the open book is open, everything is like you're able to solve if I give you long enough time, right? So shouldn't be an issue. Sorry for being hungry. Hope you feel better. I think that lady went out to get some food. So the joke here. Someone one day, little Ming go to Cambodia for a tour. Okay, and the next is he's still disappearing. Probably may not be Cambodia, maybe Thailand. I don't know. There's something interesting here. I don't know. Maybe, not sure. Can you tell me how to do question? What is question 7? I don't know if I can tell you anything. I think I already told you some of the idea, right? So I think it's fine. I mean, if the question that assignment, please ask TA, because to be uniform across section, I think he will be fair to tell you what are the hint they can give you if you struggle. Because I want it to be fair, so you can ask him if you can give you a hint. Sample paper, yes. And before I do that, actually look at my lecture notes. The exercise is already from the past papers, so you look at that, they'll be fine, already there. But I will give you at the end. But you will see it's not much different from the assignment. So, but of course, if you really want to see, I'll give you it. And okay, I can give that. Maybe I can give you earlier, because I don't want to. There's no point of keeping secret anyway. I can give earlier, but I'm not sure we have time to discuss. Okay, but I'm not giving the answer, but I'll give the question. Okay, if a time to discuss the solution, but I'm not giving the answer. Okay. Oh yes, that is applying. Okay. In the class, we try to explain the logic. Okay. I hope you explain the logic. But of course, I mean, it's like many other classes, other tech class. You can never remember all the logics, right? But at least you learn once the logic, okay, and you will read again, you understand easily. Okay, it's not the intention for you to remember all the logics. Okay, but what you need to know is under which scenario you use what. Just like as I mentioned all the analog, like the iPhone or the app, you need not know how the inner working of the app. Just to know in this situation, you press this button, will end up with what. That's like a microwave machine, right? I am able to teach you how to cook, but I can tell you, I tell you how to operate the microwave, okay? And then you know which button to put if you want to cook what. Okay, of course, I how to teach you how more stuff, but hopefully that would be fine. Okay, and I have many things black and now is because in our business application we don't need to know, right? Because if you need to know, then you're going to statistics department, right? You're taking business class, so the best thing is to know the use case, right? Because it's hard to know everything, but we try to give you some foundation why they're right. I give you say that why we have assumed normal. There's a central limit theorem here. There's a law of large number here behind what we're doing. Okay, so hopefully, after this class, okay, next class onward, basically it's more like procedural stuff. I'll tell you in this scenario, you want to do this. This is a procedure. You just follow procedure. Of course, I try to explain the reasoning behind the procedure, but without telling the proof, I can't tell you much. But at least the idea why they are right, and that's important for business, right? Because no one actually cares the technical details of course the details is important, but you need to communicate with others is the idea, right? Of a detailed matter, but our elementary class that we can't do too much. Good, everyone knows where we are. Oh, with diverse opinion on the temperature and the weather. So yeah, so the central key point is in this lecture and the this topic is basically understand how the sample mean looks like. Okay, because the idea sample mean, later you will see sample mean is a random variable. Okay, no different from previous chapter we learned. There's something, but we learn is for a bell curve. If we know the sigma, if you don't know a sigma, you'll be T. That is the main idea, main message from this one. Okay, let me repeat. The main message is the sample mean is a random variable. First, second is if we know sigma, that's a bell curve. Very nice. If we don't know, with the sample variance, that's a T distribution, and that's the three main thing that hopefully that convey. Okay. Yeah, I'm pointing to a point. Yeah. Yeah, some kind of statistics. Yes. Or Python, not yet. We'll do it afterward. So the speed is okay. Not that bad. Oh, I'm sorry about the midterm. I do understand because usually this week the lecture attendance will be very, very bad because everyone is preparing exam, and then our class open book, open notes, lecture record, so no incentive to attend lecture, but hopefully things getting better. Okay, if a person is born in a car and die outside, so let's see. Carbon dioxide. Okay, that sounds good. Oh yeah, I want to, but I mean, if you want to go, then go because you cover Python. So if you want to go, then just go. Okay, there's no harm. You don't have to stay. Okay. So if you want to go, go. But so now I want to teach some Python. In case you know Python already, you don't have to worry about it. You can just go. So I just want to teach because I think that would be important tools to have. In case you want to learn more, that tonight I will have a B.B.A lab I think that will also you can attend as well. But so this is the Python environment I'm using, and I maybe just go to the slides. That will be easier. The slides in the Blackboard already. Okay, and this slide has way more than enough we covered. Okay. But the idea is why Python, and probably many one would know. I mean, Python is the knowledge that actually you learn in programming department, and probably is a very general purpose language is applied to many things. Okay, and not just data analysis. So some of you may ask me why use Python or R. I will cover R in some other lecture. Okay, optional lecture as well. But quickly, what we do is do the code lab, so you can use your iPad to do it, and you don't have to install. And if you really want to install, I recommend you use install Anacodia. You can Google this guy. You can just download that thing. Okay, and the how to do Python offline. There are two editors called Spider or called Jupyter. Spider is like the R Studio, like the somewhat like the standard development environment. The Jupyter will be something like the code lab we are doing. Okay, later you will see. Okay, quickly why we're doing. Okay, and I'm going to explain the code lab whatever. So what we're going to do is the code lab, and by going, you can Google the code lab or type this out. Okay, now I will go to that thing. Okay, so just to remind you how to do this, is just go to Google, whatever you do code lab. Okay, and you just get in. Okay, sign in your Google account, then you can get in. Okay, I hope everyone is there. Okay, so the first thing is to have some fun. Okay, so you can see I have many animals here. So first, to take the animal out first. Okay, here go to setting, miscellaneous. Actually, you can decide whatever animal you can have, and very nicely they have Halloween style stuff. So this is good. I learned it by attending a tutorial by a computer scientist department. They teach the first one he teaches this thing. Go to this thing. So I share his teaching methodology because that instructor learned teaching award. So I guess it will be fun. Okay. So here I have an environment. Looks very complicated. So although programming is very simple. So the first thing I want to teach is how to run program. Okay, how to run your code. Very simple. Here, just very simple. I just click this one. There's a blinking thing. I can just type whatever I want. I can just start coding. Okay. So first I want to do is coding is by showing as a calculator, as a very normal. So I put 1 + 1. Okay. So this is the most simple code I have. Right. Then how to run this code. Okay. Very simple. Just a play button. Then click it. It will start to allocate. The first time you run, it will take some time, maybe 1 minute or so, but after that, it will be very fast. So what you're doing is just to connect it, okay? And once you type, it gives you the answer, 1 + 1. Okay? And of course, you can run another one, right? How do you create a one? Go to anywhere middle in the screen. Here's a code. Get the text. Code is trying to tell you add a code to run, and text is add a description. Okay. So I want to add description in the bottom first. Description. I double click here. I want it as calculator. Okay. So by doing this, it's a very good practice. Is you have verbal description and the code together. Okay, so this is what we call the IPython notebook. It's a Python notebook, so that you can have documentation and the code at the same time. Okay. So beside 1 + 1, I want say 3 - 2. I can just run. Okay, so I can do adding, minus, and I want to do multiplication or subtraction. So let me do as well. And I go around to see if any question. Okay. multiplication, and division. Okay. And lastly, I want to show you the exponentiation. Okay. So I go around to see if any question because it's more the tutorial style. I mean, if you're very good, I'm not bothered with you. But if you, in case you are working, let me know if you're working or not. So you can go to Cook Lab and iPad. Okay. If you're busy, your mind is occupied with homework or other midterm, I understand. But if any question, let me know because Python, I guess, is the one of the most useful thing in the future because as we said, Excel is going to incorporate Python there. So if you go to job market 2 years down the road, I guess most of your year 2 students, you look for a job, then you have to do Excel, and Excel will be Python will be Excel. So that's no escape. Maybe you do not need to know Python 2 years ago, but I'm pretty sure when you go to job market, you expect to know Python because you need to know Excel, right? And Python will be something there. So if you don't know, it's very likely that your job will be replaced by others because these days, the computer is very powerful. One guy can do 2 guys thing. If you're not the guy that can do the 2 guy thing, then you're out of the business. So anyway, I'm not here to lecture you what you should do, but just telling you my prediction as an economist. Okay, is that fine? Yeah, you have to get into that and okay. So now the next thing is, of course, related to statistics, right? So I have I'm not to tell you everything here. Just skip to the statistics part. There are many things, but I'm not going to cover everything. If you want to know all this, then tonight I will go to the optional tutorial that will be there. Okay. So what I want to tell you why Python is very powerful. Python is very powerful is because of the library. Okay, because it's open source. So everyone who want to use Python will put a library there, and you can use it, and that is why it's very powerful. Okay, and there's a typo here. But anything that you would imagine that is you want to do, actually Python will be there. Okay, so the thing I want to show you is how to use the statistic library that do most of the stuff that we want in our class. Okay, and then other library that I call the science lab library, that will be also science kit library that will also do the second thing. But anyway, let's tell you this one. So there's an important statement in Python called import. Okay, import actually means that I will just import that from somewhere. Okay, so in the Cook Lab, this one is already into the basic, so you don't have to import. Okay, but so what we're going to do is I would do the just type out. I'm doing statistics. Okay, and let me type out the code, import statistics. Okay, and I run this. Okay, what it's doing is trying to tell the program that I will be import a bunch of functions that will do calculation. Okay, so you don't need that in Excel. Excel is already, you cannot add anything, but Python is very good at programming is because I can import as much as I want. Okay, and if you are tech savvy, then actually you can import a lot of interesting things. Machine learning module is already there. Okay, but we just do this one. Okay, so the next thing I want to teach is in the slide is I will introduce the idea concept of a list. Okay, in Excel we store data in the in a Excel spreadsheet, right? And for Python, the simplest storage of the data is called list. Okay, and list is will be started from a bracket, a square bracket. Okay, so if I data, let me store it called X. Okay, with a two things to introduce here. One is called variable. I put a name is called X. Okay, and it will be equal to a list. It's a number. Okay, suppose this is a square bracket. I have a 1, 2, 3, 4, 5, 6. Okay, that means that I have a data which is called X. You will store 6 number. Okay, and then we will be doing that. Okay, so when I run this, it means that I have a data that's called X. Then probably you want to know, okay, what the number is. There are two ways to do it. One is go to the left hand side. That's called variables. Click on that one and wait a little bit. Here comes your X as a list, have 6 items. Okay, it tell you what the number is. Okay, 1 up to 6. Okay, and once we have the list, now we can do the calculation. Okay, for example, because I'm going to call out the statistics package. Okay, so I would have because statistics dot. Okay, that would be calling that statistics mean of X. Okay, so it immediately gives me the mean of X. Okay, and I can have median as well. Okay, so that is the idea. Okay, so in case you want another data set, I can simply actually I need not every code have analyzed. I can have a 2 line together. That's no problem because programming. Okay, so I can have 2, 3, 6, 7. Okay, that's fine. Okay, and I can also do statistics mean Y. Okay, so you can I think I didn't run that one again. Run this again. Okay, and I have X and Y here stored, so you can see by calling statistics and dot, I can call whatever function we want. Look at the menu, and this is the Y. Okay, and you can see it's not very complicated using the Python. So although I only will scratch the surface, then you can see all we learned. You don't have to go beyond Excel. And as I said, 2 years later, you will be doing this in your Excel because Microsoft is incorporating Python into Excel. So I'm pretty sure Excel function will be gone sometime very soon. Everything will be replaced by Python. So you have to know how to do it anyway. So 1 year earlier. Okay. So maybe you can try the, okay, since we have time. So, okay, let's see the last thing I want to mention, right? So you can do variance and p-variance and p-SD and SD. So what are they? It's just standard deviation and variance, okay? And P will be the population version. Okay. So before I do that, maybe I want to illustrate an one very useful function, okay, called print, okay, so that you can combine your output with data. Okay. We can call print. Okay. Why print is useful? Because when I print, I can type everything at the same here. Okay. So later you will see why I need print. Print is a function that makes our life easier. Okay. Now print. statistics, mean or not mean, p-variance of x, and I have comma, statistics, variance x. Okay, in that case, you can see when I got print here and a comma, I print out two number. Okay, that makes our code a little bit more compact. You don't need to open another code block, right? Because this one is called block, and I can add this, right? So that I can also print another one. That's no problem. Okay, instead of p variance, I can p stdev. Okay, stdev. Okay, there are four number here. Okay, as you can see, I have the p variance, population variance, sample variance, right? Populations standard deviation, standard deviation. Okay, so I just stop here in case of the question, because I don't want to be rushed, because there's already you know the basic Python from this one. Okay, if you want to know more, you can come to today's optional tutorial in the computer lab if you want to do it, but otherwise at least you know the basics of the Python, and you can go on learn more, because basically for our class, basically just learn different function, just import different library, and that's it. Okay, that's not more than that. Okay, you can basically check out the rest of the slide by yourself. You don't want to attend, but or if tonight we have the tutorial, we have the record, then you can just look at those. Is that okay? Any question? So you can see maybe just one more illustration is how can you find coefficient of variation, right? So the coefficient of variation is just very simple, right? Just use this, use the mean, right? And okay, over SD. So to do so, I can write it. This is the way usually you write. What I do is I would divide it in a multiple step. I calculate mu first with the sample or x bar. X bar, I can put the name, and I can sigma or s, right? Sigma is equal to I use the sample version. Okay, make it look nice. Okay, and then our CV, right? Or small letter CV, right? Will be just x bar over sigma. Okay, and then I want to print out the CV. Okay, but one thing I have to mention is in Python, have to be very careful about the case. Okay, uppercase and lowercase are different. Okay, so make sure that you don't confuse. Okay, so this is the last code I want to mention. Okay, and if you're done, then you can leave, because I sometimes overrun by several minutes. So today I let you go 3 minutes earlier. Okay, I stay around to answer any question you might have. This slide, this code I put it on the I put on the web. Let me switch off that first.